Okay, this is the first video on the exercise 4E1. Let's begin with some background knowledge about parallelism. Suppose you have a vector u and say another vector v, which is parallel with vector u, but perhaps, as you can see, slightly shorter. However, it doesn't matter. We can then relate these two vectors in this relationship, in this equation. And so if you can write two vectors in by equating them with into such an equation, fit them into this equation with a k is a scalar, a number, just a number, then we say that uv are parallel. So if we write this, say uv are parallel. And this is actually a two-way result. If this is the case, then we say they're parallel. If we say uv are parallel, we can then write them into these equations. And so now we use that idea to start our problem, because our task to find RS. So it means we can relate AB as follow. There's a k, and k is a scalar. And so 2, -1, 3. I jump ahead here. It's -6k, kr and ks. If you now compare first component, and therefore 2 right here on left hand side is equivalent to -6k, and clearly k is then 2 divided by 6, right? -1/3, and therefore comparing the second component, you have -1 equivalent to kr. We now know what k is, -1/3r, and therefore r is 3. And using similar reasoning, which is -1/3s, then we have s equivalent to -9, right? We'll look at one more problem right here. I wouldn't do all of them, but try to do at least one. Right, this question is just like that, and that means let's draw it. Well, all of them, as you can see, are actually parallel, but maybe they have pointing different directions, each other in the different direction. You compare them. Say, for example, look at this. We assume that simply sketch. This is AB, and we say AB is 3 times the length of CD. You get it? 3 times the length of CD. So that's why to be equivalent to AB, CD, you must have 3 CDs. That means if we cut AB to 3 equal chunks, and then we take this out, so now you have CD. That is your vector CD, right? That's nice. And how about let's try this one. The BC is 1/3 of AC, and if you want to make it simpler, you could do this. Multiply both sides by 3, and you end up with this. And this problem becomes this problem in A. That means again AC is 3 times the length of BC. The kind of 3 parts, and so this part. See, however, in this case, it's a bit different. See, they share a common point, right? And so if you look at A, B, C, D, they probably at different points. Although they are parallel, they are different points. How about this? This part D. Now surely AC is 3 times the length of BC, but if you think about it, this BC must end at C. It means only one thing. Let's draw this again, okay, properly. So AC is 3 times the length of BC, and we divide into 3 equal halves, parts, and but the vector BC must end at C and it must be parallel. Right? So no way you can place point B except by placing point B here. And so that means not only they're parallel, in fact A, B, C are collinear. This is a situation where we call a collinear situation, meaning that A, B, C are on a same line. You can draw a line which passes through all 3 points. And so this is the end of the first part. We'll do the second part on another problem later.